Hello everyone. Let us continue with the last example that we have just reached here. Z is equal to minus 1 plus 5y divided by 2. Separate divide this numerator with denominator, we get minus half is the real part of this complex number. 5 by 2 which is attached to I, that's why it is called imaginary part. Okay, this is the last example we have just studied. Let us see. X plus iy is equal to cube root of a plus ib. We have to prove that a upon x plus b upon y is equal to 4 into bracket x square minus y square. Now let us start with the given thing. X plus iy is given cube root of a plus ib. We have to solve this first equation. Whatever we are getting, just put these values in this LHS side or RHS side. We are getting the we have to prove the other side. X plus taking now cancelling cube root, we get cube on both sides. With x plus iy cube is equal to a plus ib. Therefore a plus ib is equal to expand this cube. What is a plus b cube? We know a plus b cube is a cube plus 3a square b plus 3ab square plus b cube. Okay, but from this formula we are expanding this. A cube plus 3a square b plus 3ab square plus b cube. Now we have to use expand these brackets first. X cube plus 3x square I square value is minus 1, that's why I put this value here, minus 3x, this is y square, and I cube is this. Whatever I power is, we have to convert it into square. Okay, that's why I cube is nothing but I square into I. What is I square value? It is minus 1, that's why it becomes minus I. Put this value here, minus I. Okay, now collect the imaginary and real part. We get what is imaginary part? This part, which consists of I, and which it doesn't contain I means a real part. X cube plus, this is as it is again, this is the same equation. X cube minus 3x square xy square is a real part, and this consists of I, that's why these two are the imaginary part. Taking common I from these two equations, two terms, we get I into bracket 3x square y minus y cube. Okay, now this a plus ib is a one complex number because it contains I, equal to, this is other complex number. Whole term is a complex number because it contains I. This is real part, this is imaginary part. That's why we are using the theory of equality of two complex number, which we have studied already. Equality of two complex number is nothing but if two complex number are equal, then their real parts must be equal and imaginary part must be equal. Okay, we are using this here. What is real part? A is a real part of LHS side, this is a real part of RHS side. Imaginary part is B and this term. That's why equate this real and imaginary part, we get A is equal to this term and B is equal to this term. Okay, by given thing we have solved this equation and we get A and B value. Now we have to show this, that's why A and B consist on LHS side, that's why we have to solve LHS side and show that it is equal to this number, this term. That's why take LHS side is equal to A upon x plus B upon y. This is A upon x plus B upon this B upon y. X take common and cancel with this x, we get x square minus 3y square plus 3x square minus y square. These two gets add, 3x square plus x square becomes 4x square minus 3y square minus y square becomes minus 4y square. Take 4 common, we get 4 into bracket x square minus y square, which is our RHS side, hence proof. Okay, let us move to other example. If sum and the product, sum means addition, and the product of two complex numbers are real, if sum and the product of two complex number are real, then show that what we have to find, or show that those two numbers must be real or conjugate. means if sum and product of any two complex number, it is real, not imaginary. It is real. It contains only real part, not I term is there. Then we have to show that these two complex numbers are real. These are real, or conjugate means these are conjugate of each other. If it is x plus iy 1, then other one must be equal to x minus iy in that case. Okay, in that way. Now let us start with the given thing first. Let us assume two complex numbers. Let z1 is equal to x plus iy and z2 is equal to x minus iy are two complex numbers. Okay, then sum take addition of these two complex number. First we have to elaborate that z1 plus z2 is x1 plus iy1 plus x2 plus iy2. Collect the real and imaginary part, we get x1 plus x2 plus from these two, these are all addition, we can take it on any way. Take I common, we get I into bracket y1 plus y2. This is real part, this is imaginary part. And what is given thing, sum and product both are real. This is a real. What do you mean by real? Because the meaning of this is equal to real means it doesn't contain any imaginary part. That's why y1 plus y2 is the imaginary part, must be equal to 0. Okay, this is first equation. Now take product z1 into z2, one bracket into other bracket, multiply these two bracket, we get x1 into x2 plus I x1 y2 plus I x2 y1 minus y minus I into I square becomes minus y1 into y2. Now collect the real part, x1 x2 minus y1 y2 is the real part, plus from these two take I common, x1 y2 plus x2 y1 is the imaginary part. Now this is also given is a real, is a given thing. That's why this imaginary part also equal to 0. Okay, now what we have to do, what we have to show, these two numbers z1 and z2 must be real or conjugate. Now from these two we have to solve something. Now take y2 is equal to minus y1 and put this value here, or y1 is equal to minus y2 and put this here. Let us see what will happen. Put y2 is equal to minus y1 in equation, second equation, we get y1 into x2 is equal plus x1 into y2 becomes minus y1 is equal to 0. Take y1 common, we get x2 minus x1 is equal to 0, means y1 is equal to 0, and x2 minus x1 is equal to 0 means x1 is equal to x2. This we get. Okay, now from take 1, y1 is equal to 0 implies this is y1 is equal to 0 means obviously y2 becomes 0. Therefore z1 becomes, what is z1, x1 plus I y1, y1 becomes 0, therefore z1 becomes x1 and z2 becomes x2 because y2 is 0. And what is becomes these complex two complex numbers x1 plus becomes x1 plus x2, x1 and x2, because and it doesn't contain any I value, that becomes that is two complex numbers are real, these are not imaginary. Okay, now let us prove the other side also. If x1, now we have used this, now again we are going to use this. If x1 is equal to x2, then z1 becomes x1 plus I y1 and z2 becomes x2 plus I y2. Here put x2 as x1 and y1 or y2 as minus y1, both value at a time. And what it becomes, x1 minus I y1 is complex conjugate of x1 plus I y1. Okay, that means z1 is this and z2 becomes its complex conjugate. That is two complex numbers are conjugate of each other. Second part also we have proved. Okay, now let us see the main theorem of our chapter, that is De Moivre's theorem. It's a very important theorem. De Moivre's theorem, it is very easy also. What is the statement of this theorem? If n is any real number, then cos theta plus I sin theta raised to n is equal to cos this n comes to this angle, cos n theta plus I sin n theta. That's it. This is a very simple statement of this De Moivre's theorem. So, let us see the notes. A note of depend on this complex De Moivre's theorem. Cos theta if plus if middle sign is minus, if cos theta minus I sin theta raised to n, then it becomes cos n theta minus I sin theta. Simple. Okay, middle sign also same. Just replace by theta by n theta. If cos theta plus I sin theta raised to minus n is there, then minus n comes to angle, we get minus cos of minus n theta plus I sin of minus n theta. And we know cos of minus theta is plus cos theta, and sin of minus theta is minus sin theta. That's why it doesn't matter where cos becomes angle becomes plus or minus, it remains as it is, cos n theta. But for the sin, it becomes minus I sin n theta.